Hi, well I thought it's time to have a play with this camera and see if I can get it to do anything useful. Now I've very kindly been lent the PCI card, which was missing from my system because the computer wasn't there. This is the card that Spectral Instruments supply for interfacing their cameras. It supports both the fibre optic and also the parallel interface. This is an RS422 interface with sort of 16 pairs of data. It seems to have the option of 422 or fibre interfacing. This is fairly straightforward. There's a Xilinx Spartan 2 FPGA. There's the Cyprinx Hotlink transceiver. Interesting, they're using the quad version of the transceiver. Perhaps they were planning to have a version with multiple parallel fibre streams, or perhaps it was an availability issue because the Hotlink devices are obsolete, so perhaps they were having some obsolescence issues and had to use the quad one on this card. There's a Xilinx CPLD here. There's a FIFO memory to sort of handle the buffering of the data, PLX PCI interface. And there's also a UART because on the RS422 version it uses UART as a communication channel for setting up the camera parameters, etc. Whereas obviously on the fibre one everything goes down the fibre optic. Now there's a few other odds and ends. I was sort of reading through various bits of documentation that a few people linked from the previous video. When these cameras are shipped, they get shipped with a couple of files which are specific to that the configuration of that camera, because obviously these cameras come in different versions with different CCDs, etc. I ended up phoning up Spectral Instruments and they kindly sent me the camera specific files for this camera, and sort of managed to start talking to it. I got all the cooler and the vacuum sensor and everything up and running, and also I got the rubber O-rings to replace these seals. And I think a couple of YouTube commenters said that these are called a Helicaflex seals. I'm pretty certain this is aluminium. And sort of looking at their website, they do a series called the HN200, so that's probably what these are, but I haven't made any inquiries as to replacing these, so those rubber O-rings were very, very cheap, so just stuck those in for the moment. So I'm still not totally sure whether these are designed as a one-time seal, or because these actually do have a you see there's actually sort of coiled spring inside. So the idea is that this compresses down, but there's a little bit of springiness coming from that coil to sort of keep it compressed. But just for simplicity, I put the rubber O-rings in because those will provide a sort of reasonable seal. And looking at the figures I was getting, it is holding a reasonable vacuum, certainly to start playing around with it. And of course you don't actually need the vacuum to be there. The CCD will still run, it will just run a bit warmer and be a bit more noisy, so that wasn't really a particularly high priority at the moment. Now when I got all the software up and running, I wasn't really getting much sense out of the images. It was clear that what I was seeing had some relationship to the amount of light coming through, but it really wasn't anything anywhere near a coherent image. And just by chance, because I was running this thing with the cover off, so we didn't have this fan running, I just wanted to just sort of quickly check to see if anything was getting ridiculously hot. So I just had a quick look using the thermal imaging camera, and I noticed that 3 out of these 4 chips were getting extremely hot. Now, just sort of looking a bit more closely at this layout, it's quite obvious that these are actually 4 identical circuits. Now, of course, the CCD itself is divided into 4 quadrants. Now, I was assuming this was just really for readout, but I think it may well be that the CCD is almost sort of 4 completely separate CCDs on one die, and it's got 4 sets of drivers driving it. So obviously, if we've got 3 of them getting very hot and one not getting hot, then that sort of really points to the fact there's possibly something not quite right here. So, well, my first thought, well, maybe perhaps there's a problem with the CCD itself. So I unplugged this and just ran the board on its own. Basic MOSFET drivers, which are designed to provide a fairly sort of reasonably strong output drive for a capacitive load. And these were driving, I think the power supplies on these were -10 and +3 volts. So it was producing an output swing between -10 to +3, and I think they've got some level shifters on the input to get the logic level to the right place. Each of these are dual drivers, and on the 3 that were getting hot, one of the 2 outputs was clearly not outputting what was being driven into it. So that was just a very lucky spot on the thermal image, just purely the fact that of 4 identical circuits, 3 were getting hot and 1 wasn't. That really rang alarm bells that there was clearly something not quite right here. And how they got that into that state, I don't know. I thought those were just driving the CCD, but just a quick check, I just swapped 2 over just in case there was something else on the board that was causing it. But you can see from this image that clearly the fault moved with the chip, so it's definitely the chip and not the board that was faulty. So I ordered those up, replaced them. The temperature that then looked fine. There's still some hot spots on the regulators, but so these are all linear regulators, and you expect these to run fairly warm. So when I was testing it, I was sort of putting it face down, but I just had it, obviously wanted to put something soft underneath it to protect the front plate, and it just purely happened that I was using this Vision Engineering sort of cleaning cloth that had some printing on it, and it also just happened to have some fold in it. And I was noticing that I did actually occasionally get something that looked like a sort of vaguely sensible image. This is the default settings, which is a 1 second exposure. It takes it does take quite a lot of time to download it. Now you see here this one, you can see some very clear details of that fabric, so it clearly is seeing something, but you can actually see some of the text down here. But it's very, very sporadic. If I acquire another image, chances are it's going to look completely different. Yes, I mean that's just completely different. There's still some evidence there, but something is clearly sort of varying a lot. The other thing I noticed, if I change this to dark exposure, what this does, this takes an image but without opening the shutter. Obviously the shutter's an electronic feature on there. So in principle this should be a fairly blank, flat image, which is obviously used to subtract, a lot, to generate, subtract all the offsets and do some of the defect compensation. But I was noticing that even with dark exposure, I was still seeing some evidence. For example, there, I mean, that's almost, there's almost no difference. The other thing I noticed was that if it got a very, very bright image, it would sometimes actually almost fold over from white to black. So if I'm just going to tilt this up a little bit just to let a bit more stray light into it. It seems to sort of, I think, there's some saturation and maybe amplifiers overloading and so on going on. It just tends to go sort of completely crazy. So I was sort of going down to a much shorter image exposure time, sort of one millisecond exposure. Certainly does decrease the sensitivity, but what was very interesting is that it did seem to be changing from frame to frame. Yes, I mean, but also you do see very noticeable differences in certain quadrants. As far as I can tell, the 4 sections of the CCD are, possibly completely independent. There certainly seem to be 4 sections on the drive circuitry, and there's obviously 4 outputs. But this part of the image looks vaguely plausible. Again, I'm just tilting this a little bit to let some light through. But then this one is totally different. What was annoying is this sort of about 5 seconds it takes to read back. It was quite difficult to purely by the amount of time that I was taking. It was quite difficult to see what was going on. So what I did was, if you actually just you can reduce the area of the image that it reads out. So instead of saying 2048, let's just read 512. We'll add a bit of an offset on there so we're not reading sort of quite in the corners. The image won't be a sort of whole coherent image. We'll probably see 4 quite different sections. But what that should mean is that we should be able to read it back more quickly. So I now do, again, we're still on the 1 millisecond exposure. That's now sort of taking only about a couple of seconds, maybe 2 or 3 seconds to acquire. One interesting thing I noticed is this: we can actually see this hexagonal pattern, which I'm pretty certain that is probably the actual structure of that fibre coupler. It's similar to the pattern we saw on the plate, but I don't think there's like any residue of the plate sort of stuck to there. I suppose it's conceivable there might be. I can't see anything obvious, but I suspect that's probably the actual structure of the fibre optic coupler. But as you can see here, we can get in some images. Obviously, we've got a certain amount of noise and dead pixels and whatever. Bear in mind that these images haven't been compensated for the default black, because we can't seem to actually take a dark image. If we do a dark image and then an image and subtract that should make a lot of this rubbish go away. But this is making me think there is some issue with the CCD timings, possibly intermittent, or maybe something like, if I put them continuous. The sort of randomness sort of suggests to me it's sort of that maybe it's something like a floating input or something. So I think what I need to do is actually set this up acquiring as fast as I can, and then maybe just do the old sort of finger test, run a finger around the board and see if there's anything that makes it go completely different. But all I'm doing, I'm just not doing anything at all. So we are getting this sort of breaking. This is because we're only reading a subset of the image. It actually seems to be a little bit more consistent. If I just don't touch that at all, it does actually seem to be reading it back fairly consistent. If I just spin it around a bit to remove the position of that cloth, you can now see it's changing. But it's actually quite a bit more consistent from frame to frame than I was noticing before. Okay, so having played around with this, I think actually all that inconsistent was simply due to the fact that whenever it gets even a small amount of overload in terms of light, it just splatters all over the place and does all sorts of weird stuff. And because I just had this thing just basically sat on the bench, sitting on a cloth and just wobbling it manually, just a small amount of variation in light was causing it just suddenly swamp and show just complete garbage. So I'm pretty sure that the only thing that was actually wrong was those 3 drivers. I can't really imagine how those got into that state, but it does actually seem to be producing sort of sensible, reasonably coherent images now. So it's probably as much my ignorance and lack of experience in CCDs assuming that this sort of weirdness was some hardware fault, whereas actually it was just behaving normally. It's just rather sensitive to excess light levels. Okay, I've just put this very crude lens mount. This is a standard CCTV lens, which obviously is going to produce an image that's far too small. Sort of just a piece of plastic with some black foam on there just to isolate any stray light. I've had to close this literally, this goes down to sort of f16 and then there's a closed position, and literally I've had to just back it very, very slightly off close, so there's a tiniest little pinhole, and I've cut the exposure right down to 1 millisecond, and we do actually have a vaguely coherent image. Interestingly, here where it's seeing one of the lights, again we've got this sort of big streak across it, so I suspect this thing is probably going to get freaked out by any sort of major variation in light levels, but we do actually have a complete image. Okay, I'm now actually getting some fairly reasonable images. Now this is with a 100 millisecond exposure, and this is basically with all the workshop lights turned off. Pretty much the only thing that's illuminating that is the stray light from this monitor. I'm sort of looking over here at this bunch of random screwdrivers and so on, but yeah, in this light I can see it, but only just. It's pretty dark. Literally, it's pretty much only the reflection from this monitor that's lighting that. See, this lens is only illuminating a part of the sensor, so I'll just zoom in on that section. So you can see we've actually got sort of quite a nice sort of clear image. It's fairly sort of even over the quadrants. We are seeing a slight trace of this hexagonal pattern. So it's pretty obvious I'm going to need to figure out some sort of better lens arrangement than this. In terms of sort of what's available off the shelf, a medium format camera would be about the right sort of size, but I might just be able to improvise something. So while I'm having a think about that, I just want to have a quick look to see if I can find any more information about this CCD. Now, the configuration file I sent for this camera identified the CCD as a CCD 6161. And this turns out to be a part made by Fairchild Imaging. Needless to say, I couldn't find a great deal of data about this apart from this summary page on a different website, and basically saying it's 4K by 4096 by 4096, sort of designed for advanced scientific, space, industrial and commercial imaging applications. And the pixel size is 15 by 15 microns, just under 61.5 millimeters square image area with a 100% fill factor, so no major gaps between the pixels. And I was trying to hunt around to find some sort of cost information. I found this is actually a doctoral thesis. This is about the design of a liquid mirror telescope that uses a rotating dish full of mercury, about half a ton of mercury, to produce an adjustable mirror. I'll put a link to this paper down below because there's quite a lot of information about how CCDs work and various other aspects of this. So it's actually quite an interesting read. And they actually did a review of 2 different CCDs, including this one, and they list their price of €75,000. But these chips are available in multiple grades. That price refers to a grade 1, which is sort of the second best grade. For an application like the genome sequencer, there's probably quite a lot of scope for eliminating a lot of the errors during the processing phase. So and also there are quite a lot of visible defects on the images that I was seeing, so this is probably a lower grade than the one they were looking at. And so I have heard another figure of about 20,000 quoted for an X-ray type application, but it's still a very expensive piece of silicon. Of course, although it's very expensive to buy, doesn't necessarily mean it's got anything like that value, because of course anybody that's got a genuine use for that sort of CCD isn't going to be going to sort of buy one on eBay or anything like that. This is common on a lot of sort of very high cost things, particularly things like FPGAs. You see sort of people on eBay who've got a load of new old stock FPGAs. They look up the price on DigiKey at like a few grand each and think they're actually going to get that, but anyone that's using that sort of level of part isn't going to be buying them on eBay. So there's a somewhat massive depreciation on stuff like this. But obviously if you are wanting just to tinker and mess about, then if you're lucky there's a potential for getting a completely unaffordable thing at a very sensible price. And particularly in the case of these genome sequencers, because of the chemicals are no longer available, there seem to be quite a lot of these coming out on eBay at the moment. If you're looking for a very high performance called CCD camera, they are out there for peanuts. If you want them, just make sure you get the PC with it so that it's got the capture card there. I think we are going to see quite a lot of these, and it would be nice if these cameras could actually use for something useful. Astronomy is one obvious option, one obvious thing, but obviously one issue there is that this is quite a big, chunky, heavy camera with a fairly large imaging area. So your average telescope, the mount is going to have to carry the weight of the camera, but also the optics need to produce that 61mm square image. So I think we're possibly looking at more sort of homebrew telescopes and strapping this onto an off-the-shelf telescope. I just realised that the quick solution to the lens and field of view issue is just to do a pinhole camera. So I've just got a couple of bits of pipe, a bit of foil over there with a pinhole in it, and then I can sort of insert this either way around and get different distances to experiment. Okay, I've got this slightly ridiculous pinhole camera just pointed at some random bins on the wall. I'm having to use a 10-second exposure because obviously the pinhole is so small that it's not letting much light through. I've got the cooler switched off at the moment just because it gets quite hot if I leave it on there. I haven't got the heatsink on there. But there's one issue that was literally I've been trying to figure out for about the last hour. What I was seeing is whenever I took a photo, it appeared that I was seeing remnants of the previous image in that photo, and then I took a second one and then it appeared to be the scene that it was pointing at. And I was trying to figure out what on earth was going on. And then I sort of did a couple more experiments, and I realised what was happening. It was actually, if I had it pointed at the scene, I then sort of put something in the scene when it wasn't taking an image, took it out, then took an image. I was seeing some of that, that thing that was on the scene. So I was just making the assumption that when I was sort of starting an image acquisition, that it was actually starting afresh and clearing everything. Because of course the thing about CCD is it's like a charge accumulation device. There's a good analogy I saw somewhere that said if you think about light as being rain, the CCD is just a big array of buckets, and obviously to start that acquisition you want to empty all those buckets. So I figured out, well, hang on a minute, what's going on? It looks like the CCD wasn't being cleared when I started an acquisition, which I naively assumed that it would clear out everything at the start of a new acquisition. And eventually I was sort of looking through all the settings and menus, and then I actually found this option that says continuous clear, which was actually disabled in the configuration file I was using. Once I'd enabled that, it then worked as I'd expected. I could say, so stick my hand in front of it, take an image, and then we'd see that image with nothing from the previous image. Now obviously this image looks pretty horrible and grainy and nasty, but bear in mind there's no corrections at all been added to this. Obviously this is completely raw data from the CCD. If I just put a piece of black right in front of the pinhole, so it's seeing no image, no intensity at all. This gives us our background level, so you can see on the histogram we've got a fairly narrow spike down at the black level, so we can just tell it to use that as the background. And similarly at the high end we can give it a fairly uniform field of white to give it the upper level, because as well as an offset on each pixel, there's also potentially gain differences between each pixel, so you can basically calibrate those two out to get a more linear image. So I was struggling to think of how to get a fairly uniform white light image. I ended up figuring out, well, LCD screens are quite uniform, so I just sort of got a screen full of white and stuck that in front of it. Now, interesting, this image, we can see although what I was showing, it's sort of a nice flat white image. Now, there may well be some distortion from the fact we're using a pinhole, but I suspect what's going on here is that it's that fibre array. If you imagine you've got this sort of bunch of fibres, and I suspect that the sensitivity is somewhat dependent on the angle of incidence of the light onto that fibre array, because obviously all the light's coming from this pinhole in the centre, so that the stuff in the middle is going straight up onto it, but the stuff at the side is hitting it at an angle, and I suspect that is why we're getting this pattern. But let's just set this as the flat field anyway. That will also apply to the image we're trying to look at, so although that's not a completely flat field in terms of the CCD, it's the same as a flat field coming in from what we're looking at, so it should actually correct for that. So if I now tell it that's the flat field image, if I now acquire another plane image, again, so this is the raw image with all the with all the noise and crud on it, but if I now apply that correction, we now see we've got a much cleaner image. We've still got a few sort of noise dots here, but yeah, almost all of that noise has disappeared now. Now what I'm going to do now is turn the cooler on and see how much difference that makes. The cooler does actually work surprisingly quickly. This is real time, so it's already down to 10 degrees. Obviously this is the temperature at that copper coupler onto the back of the CCD, but within a minute or so it's down to 0, so it doesn't really take that long. But obviously the CCD itself will take a little bit longer to cool down, although it's made of ceramic, which is quite thermally conductive. But I'm going to leave that for a few minutes just to get down to temperature. Looks like our vacuum is still reasonable. It's got, I think it was about, got it down to about 2 torr when it was on the vacuum pump. It's come up a little bit since there, but it seems to be holding reasonably stable. I pumped it down about 3 days ago, so that rubber seal does seem to be holding. Right, this has been running for a few minutes. CCD is now down to minus 13.7. Obviously the pressure has also dropped because of course it's cooling down, so the air's contracting. The backplate temperature is up to 48. I haven't got the big heatsink or fan on there, so I suspect that may actually limit how cold this will go, because obviously if the hot side of the Peltier is at a fairly high temperature, that's going to limit how cold the cold side would get. So with that massive fan and heatsink, that'll probably get at least 10 degrees less. Let's just see if that makes any difference to the image quality. So again, if we repeat our flat field compensation, so that's our black image. Interestingly, we also have this sort of dark zone in the middle. I suspect that might just be a tiny little amount of light leaking in from somewhere, and again being perhaps distorted by the fibre array. And that's our light image. There's a little bit of streaking there. We might be on the point of overload, although we're only getting up to about 4,000 on the histogram, but let's use that as our flat field. These images do look a lot less noisy. These are just still completely uncorrected images, but we're getting a lot less visible noise on there. So if we now take our raw image, again, and that's our raw image, that's looking much cleaner than it was before. And we then do our correction. Again, there's almost no spots at all on that image now, so clearly running that CCD cold does make a very significant difference. And in fact, looking at some of the other cameras in their product range, they do some where you can use an external cooler. It's got like sort of 2 pipes on the back for running coolant through, and they can run down to as low as minus 100 degrees C. This is more of an issue as you get to long exposure times, as the noise starts becoming a significant issue. We've cooled it from about room temperature, I think it was about 20, down to about sort of minus 15 or so. So those 45 degrees make a very substantial difference to image noise for long exposures. Right, I've managed to get it down to minus 22.5, and this flat field image is almost spot free. There's just a few odd little spots here and there, but nothing major. So let's do an acquisition in this mode. So this is the raw image. So there's a few odd little spots here and there, but really nothing that much. If we apply the correction to it, then I can't actually see any spots at all. Again, look at the overall image, that's pretty much completely spot and noise free. I don't know how good this CCD is in terms of defects. The cameras are supposedly supplied with a defect map, which I haven't got, so I don't think there's actually any bad pixel correction going on here. There's a tiny little spot there. Bear in mind there might be a little bit of dust on the face of that fibre coupler. Down at sort of minus 22, this image is extremely clean. So what I'll do is I'll let it warm up to room temperature and just take continuous exposures, and just to show dynamically what the effect is of the noise as the temperature increases. So another possible use for this camera would be for an X-ray detector. Now, compared to the sensor that's in my Faxitron microfocus system, The resolution is higher, it's 15 micron pixel versus 50 micron for the Hamamatsu sensor, and it can potentially do long exposures. The software that comes with the Factotron has a limit of 20-second exposure, so there would be a potential to increase that, and it may or may not be more sensitive. Obviously the long exposure might give you some additional effective sensitivity. Now there's a few issues with doing this. Obviously one is just the physical size of the camera. To get the same range of potential for geometric magnification, I'll probably just have to chop a hole in the bottom and mount the camera underneath it, which would be a bit of a pain. But the other is the actual scintillator. At the moment I've just stuck a bit of, this is just some plastic film from an old Kodak X-ray cassette. I also had to surround the sample with lead because light from the scintillator around the outside of the sample was tending to saturate the camera, and obviously this camera is much more prone to saturation than the Hamamatsu sensor. I think the issue here is, and it does work, but I think the issue is that the scintillator that I'm using at the moment, because it's fairly thick, is just blurring it. I think what I really need is some sort of very thin film of scintillation material. Now I don't know to what extent that's available, or things that are designed as X-ray sensors have it coated on as a very sort of thin film, so I don't know if anyone knows if there's a scintillator material for 35 kV X-rays that is available like just as a very thin film that I could just stick on the front of this. Then please let me know. But I think at the moment that's really the limiting factor. The two problems with this Factotron aren't really image resolution. It's firstly the fact that it's only got a very small sort of 50mm sensor, but also the fact it's only 35 kV, so its penetration power isn't that good. So although this might make although this might work, it's probably not going to add a huge amount of usefulness. But on the other hand, if you've picked up a Factotron and don't have the sensor or don't have the system that the sensor plugs into, then picking up one of these cameras in a genome sequencer might actually be a viable option to get something up and running. I actually found a little bit of the scintillator from the sensor from that X-ray CT took apart a while ago, and that is actually a fairly thin film on aluminium, sort of what looks like aluminium tape. That gave slightly better results, but of course we've also got this hexagonal pattern from the fibre coupler to deal with. Obviously the other issue is that this isn't designed for X-ray specifically, so we might get some X-ray interference on the sensor, although it's got a pretty big chunk of that fibre to go through, so at 35 kV I doubt that much will actually get through that. So interesting piece of kit, and if you have a need for one, then they're clearly available crazily cheap. The question is, how many people actually have any use for a cooled CCD camera? So the only things I can think of are potentially for X-ray detection, but probably slightly more mainstream astronomy. But I don't know enough about the optics and what the state of the art is in relatively low cost cooled cameras for astronomy these days. But if anyone does sort of get hold of one of these and finds a use for it, then please let me know, because I'd be quite interested to see a real application for it.